Hello everyone, it's Abhishek here. In this video, I am going to explain the SAP-1 architecture in brief. Let's look at the circuit first. Here's the SAP that I have added. Here's the program counter, and here is the RAM. Here's the register general purposes, register A and register B. And here is the instruction registers. And here is the control sequencer that controls the sequences. Let's dive into the main circuits that I have built in Logisim. Here is the register general purpose, which we are using in accumulators and register B. Here's the input control, and here's the clock and output controls. And on the right side we have internal output and outputs, which helps us to display the outputs that we have. Here we have the ALU, which is arithmetic logic unit, which calculates out the values like addition, subtraction, all of these. So this have input 1, ALU in 1, and ALU sub, which controls the subtraction. If it's turned on, then subtraction, and if it's turned off, then the addition will happen. And here is the carry output, and here are the all outputs that we have. Now let's move on to the program counter. In the program counter we have clock, reset button, and output control pin, which enables the counter output, and we have count control. And we have another circuit, which is 4x16 decoder, which controls just 16 values by controlling these 4 pins, which is 2 to the power 4 is equal to 16. So decoder is used in our circuit. And now let's move on to the SRAM cell. Here is a single SRAM cell which values 1 bit. So here is the SRAM, and here is the total 16-bit SRAM cell. Here is the whole SRAM. Have a look at it. And then we have instruction register. Then we have instruction decoder, which decodes the programs, like whether halt is happening, or whether it's adding, or it's loading A or loading B, something like that. Then we have ring counter. It is the ring counter circuit. And lastly we have control sequencer circuit. Here are all the pins, input pins, and here are all the output buttons. Now let's move on to the main circuits. Before doing anything else, let me explain the input buttons. Here is the B out button, which outputs the input values that we have on the B register, that displays that output. And then we have ALU subtract button. If we turn that on, ALU will do the subtraction. And then we have an important button, which is control sequencer enable button. By enabling it, we can enable the control sequencer to count the sequences. Then we have marine enable. Marine enable, it's manual because we are doing it everything manually. So in the marine enable button, we can select which addresses to put the values. Like for example, if we select these address to store value, then we can turn on this and give a clock pulse. Then this address will be. After that we have SRAM write manual. After selecting this address with marine enable pin, we can now put this value into this address. So with marine enable, this address is selected, and with write manual, we can, with the PC reset button, we can reset the program counter button, program counter output. And this is the most important button, which is clock. and we have a debug pin, which is, if we turn that on, the debug data will flow through here in the bus. And we have the debug data which will flow in the bus, and that's it. That's all the button. Now let's move on to the manual mode. We're doing everything manually here, and after that we'll do it automatically. Now first let's understand what we are going to do here. We are going to do load A, which means we have some values and we want to add those values and put the values into some of these addresses. So for example, here I have the addresses and instruction binaries. Now let's move into the circuit. Before doing anything else, I will turn on the control sequencer enable button, and then we'll do the PC reset, and then give a clock pulse and then turn it off. Now before putting the debug data here, we have to debug pin on, then turn it on. After doing the debug pin on, we can select this address to put the data here. So we can put the data like 1 1 and give a clock pulse to it. Before doing that, we have to do the PC reset and clock pulse because it's for safety purposes. Now let's move into the mine section, which will select the data and put the data here. Now in the image we have seen that these are the addresses, binary addresses, and these are the instructions. So we have to select these addresses by marking enable and then put the instructions here by selecting the SRAM write manual button. So let's do it one by one. Let's select the first address by enabling the mark-in enable button. Before doing that, we have to give the data. Here the data is given, which is everything 0. Now let's mark-in enable and then give a clock pulse. After doing that, this 0000 address is selected. Now we can put the data in here. So let's put this data, and it is 0001 1101 0001 1101. To write this data into here, we have to click the SRAM write manual button and give a clock pulse. As you can see, the data has been written here. Now by doing this, we can put all the datas, the rest of the datas here, and let's do it one by one. The next data is 0001, so let's put everything off 0001 and mark-in enable. Let's select the address and then put the data, which is 00101110 00101110, and then SRAM write manual. You can see the second data has been written. Now let's select the mark-in enable. This third data has been selected, which is 0011 SRAM write, give a clock pulse and turn it off. As you can see, the third data has been written, and the fourth address is 0011 mark-in enable. Can select it, turn it off, and put the data into the fourth address, which is 0101 41. Then SRAM write, clock pulse, the data has been written. And the fifth address is 100, which is 01 1011 and 1000, which is 100. So we are putting the data into the 100 address and select it with more in a novel, and then give a clock pulse, turn it off, and the data has been and the address has been selected. Now we have to give data, which is 4140 4140. Now let's write it with SRAM enable. The data has been written. Now let's move on to the data values in RAM. We have to select the addresses from here and write it with these datas, which is 19 and 47. So let's write these datas. First we have to check whether everything has been turned off. Yes, everything has been turned off. Now let's put the address, which is 401101 401101. Let's select with minor novel clock pulse and give the data, which is 0001 0011 0001 0011. SRAM, right, and the data has been written here. Turn it off. Let's select the next data, which is the address is 00001110 1110. Select it, clock pulse, turn it off. Now let's give the data. The data is 001041 001041. Write it with clock pulse, and the data has been written here. Now turn everything off, and after putting all the values we have to turn everything off. Now as you can see, the data has been written here, and we can see the 5 instruction has been given here. So now we have to run everything, run the program with giving the clock pulse. So before doing anything else, we have to turn the debug pin off, which turns off the flowing the debug data here in the bus. After doing that, we have to reset the PC for ons. Yes, the PC has been reset. So after doing the PC reset, we can follow the 5 instructions. Now for each instruction, here are 60 states, which are fetch, decodes and executes. These 3 steps count 60 states. So for this we have to give 6 clock pulses for each instruction. Now let's start. Now let's give the 6 clock pulses and see the data here. 1 2 3 4 5 6. As you can see that the load A has been followed and the load A instruction has been executed. Now to follow the next instruction, which is load B, we have to give another 6 clock pulses. Now let's do it. 1 2 3 4 5 6. As you can see, the load B has been done. So after doing that, the addition has to be done. Give another clock pulse. 1 2 3 4 5 6. As you can see, the data has been put in the A value, which is adding the values, these values, into here. Now let's give another clock pulse, 6 clock pulses, to put this address into here, which is STM, means store the values into here. As you can see, the data has been written here, and then the execution has been done. Now we have to stop the program. To stop the program, we have to give 3 clock pulses. 1, 2, 3. As you can see, the program counter counted another value, which is 101, and the program has been executed successfully. That's it. I hope that you understood everything what I have done. You can do it manually by hand on your own computer. In the previous section, we have seen the SAP-1 implementation by doing it manually. So in this section, we are gonna do it with automatic way, which needs a ROM and an instruction loader. You can see right here. Here is the instruction loader. Let's move on to the main section. So before doing anything else, let me explain the process here. Now first we're gonna turn on the debug pin on, and then give clock pulses for these addresses to load here on the debug data. So here are 16 datas. So for 16 datas we have to give 2 clock pulses. So if we give 32 clock pulses, the data will be loaded here. So before doing that, let's move on to the hex codes we have to give into the ROM. Now here is the GitHub repository which I made. This is the whole implementation of this SAP-1 project. So by scrolling it into the section, we can see the assembler or compiler section. I have added the link here, which is the web app here. As you can see here, if we give the assembly codes for adding the data which we have seen in the previous section, like a load A, load B, or add, storing the data, halting the program, and the giving the decimal values. So if we put this assembly code, let's just copy it and paste it into the Streamlit version of the app. So if you paste it here and click the assemble to hex button, we can see the data here. So let's just copy it and paste it into the ROM. Let's right click it and edit contents, and let's just make it bigger and let's paste it here. So we can just close the windows. As you can see, the data has been pasted here. So by pasting the data, we can now keep clock pulses and put the data into here by giving 32 clock pulses. So before doing anything else, we have to turn the debug pin on because the data will be flown here. So let's give the clock pulse. As you can see, the data is being loaded here automatically, and as you can see, the marker is moving through this line. As you can see, the data has been loaded successfully into the RAM, and you can see the starting address in the data bus. So let's just turn off the debug pin, and now let's explain the process. We have 5 instructions here written here in 7 lines. So for executing these 5 instructions, we have to keep 6 clock pulses for each instruction, which in results 30 clock pulses for the whole process. Now let's do the PC reset. 2, 3, 4, 5, 6. As you can see, the data has been loaded here. After 6 clock pulses, the data in register A has been loaded, which is 13, which in decimal is 19. So now let's load the register B with 6 clock pulses. 1, 2, As you can see, the data in register B has been loaded here. Now let's give another clock pulse. As you can see, the add, the addition, the sum has been stored in the register A. And the register A, the value in the register A has been stored in the address 15. So the program has been executed successfully. Now I have to halt the program. So we can click the clock pulse for 3 times to halt the program. As you can see, the counter value has increased. The program has been run successfully. So this is it. This is the complete implementation by doing it manually and automatically. I hope you enjoyed the video. I hope you learned something. Have a good day. Signing off.